All right, let's talk about the future of power. We're diving deep into two incredible nuclear technologies that are both fighting to solve one of our biggest global challenges. On one hand, we've got the next step in nuclear fission, an evolution of what we have today. And on the other, the revolutionary, almost sci-fi dream of nuclear fusion. So what's the difference, and what could our future actually look like?
So why all this effort? Well, it all starts right here. Our planet has a massive and growing appetite for power. We're on this huge quest to find an energy source that's not only clean and abundant, but can also power our entire world without, destroying it.
And this really boils down to one central massive question. How do we get energy that's clean, totally reliable, and completely safe, running 24/7, no matter if the sun is shining or the wind is blowing? It is a really tough puzzle to solve, but nuclear technology has some pretty compelling potential answers.
To figure out the best way forward, we need a way to judge these technologies. Experts talk about something called the energy trilemma. It's basically this constant juggling act between three things we absolutely need: sustainability for the planet, rock-solid reliability for our grid, and of course, safety for all of us. This trilemma is the perfect lens for us to look at our two contenders.
Okay, first up, let's look at the evolutionary path. This is all about perfecting the nuclear fission technology we've been using for decades. Welcome to the world of Generation 4 reactors.
So what exactly are Gen 4 reactors? Well, don't think of them as a total reinvention. It's more like taking a proven engine and giving it a massive, futuristic upgrade. Gen 4 is really just an umbrella term for a whole bunch of new designs that take everything we've learned from 60 years of nuclear power and push it forward, with a huge focus on being safer, way more efficient, and a lot cleaner.
Now here's where it gets really cool. Gen 4 reactors directly address the biggest criticisms of older nuclear plants. They have what's called passive safety, meaning they can shut down on their own using the laws of physics, not because a person hits a button. They squeeze way more energy out of their fuel, and get this, some can actually run on the nuclear waste from older reactors. Plus, they run hot enough to power heavy industry, like making steel or hydrogen, which is a huge piece of the decarbonization puzzle.
And this isn't just one single idea, it's a whole family of them. I mean, look at this table. You can see they're trying all sorts of different things, using coolants like liquid sodium or molten salt instead of just water. Now, don't worry about the technical jargon here. The real takeaway is just the sheer diversity of innovation. This isn't one single bet. It's a whole portfolio of research trying to perfect fission.
All right, so that was evolution. Now let's talk about revolution. This second path isn't just a different idea, it's a complete paradigm shift. We are talking about nuclear fusion, the thing many people call the holy grail of energy, because it's the exact same process that powers the sun and every star in the universe.
So if Gen 4 is like upgrading a car engine, fusion is like trying to invent a warp drive. It's a whole different ball game. Instead of splitting heavy atoms apart, fusion takes really light ones, like types of hydrogen, and smashes them together. And when they merge, boom, they release an absolutely incredible amount of energy. We're literally trying to build a tiny star right here on Earth.
And this slide just lays it out perfectly, right? Fission takes something big and heavy, like uranium, and breaks it apart. Fusion takes something super small and light, like hydrogen, and builds it up. Two totally opposite ways to unlock the power hidden inside an atom.
So you might be wondering, why go through all this insane trouble? Well, the potential payoff is just huge. The main fuel can be extracted from plain old seawater, which means it's basically limitless. The process itself is inherently safe. There's no chain reaction, so a meltdown is physically impossible. It produces zero long-lived radioactive waste, and it gives you more energy from less fuel than anything else we know of.
Okay, the promise is unbelievable. It sounds perfect. But now it is time for a little reality check. Forget the hype for a second. Where do these two technologies actually stand today?
This timeline tells a huge part of the story. You can see that Gen 4 demo reactors have been running for decades, with more coming online right now. We're looking at commercial designs in the early 2030s. Fusion, on the other hand, just hit a massive scientific milestone in a lab recently. But the really ambitious targets for the first pilot plants that actually put electricity on the grid, well, that's still way out in the 2040s. That's a big gap.
Yeah, this has led to a long-running joke in the science community. Fusion is the energy of the future, and it always will be. It's a bit of a lighthearted jab, of course, but it points to the absolutely monumental engineering challenges we still have to solve before fusion power is a real commercial thing.
So
Let's put them head to head. You can see it clearly here. Tech readiness, fission is near-term. Fusion is long-term, still experimental. The waste, fission's is much improved, but fusion promises no long-lived waste at all. And this brings us to the biggest hurdles. For Gen 4 fission, honestly, it's about economics and getting the public on board. For fusion, the challenges are still fundamental. Like, how do you keep the reaction going and build a machine that doesn't just melt?
So, after all that, where does this leave us? Well, we have two very different paths, but they're both aiming for exactly the same goal: clean, reliable, 24/7 power for everyone.
And maybe this is the most important takeaway of all. This doesn't have to be a race with only one winner. It's not an either-or situation. It's actually really likely that these two technologies could work together. Gen 4 reactors could be a crucial bridge technology, helping us decarbonize over the next few decades, while we continue that hard, essential work to finally unlock fusion's revolutionary potential.
Which leaves us with one final thought to chew on. When we look at our clean energy future, what's it going to be? A steady evolution of the tech we already have, or a complete revolution that changes everything? Well, based on everything we've seen, the answer might just be